URL in Discord real quick. But it's basically just a blank new project. There's really nothing in it, but it does have some dependencies. So text, vector, containers, random, monad loops, and arithmoi. So if with your build system of choice, I'm using Stack today, you want to clone this. If you clone the project, you can use Stack and then just run Stack setup and then Stack build. You should be able to follow along with all the examples as we go. And some of these will be working together as a group, and some of them I'm going to leave to you as exercises, and I'll be helping out. And basically, our goal for today is we're going to run through a series of like fairly simple, already very broken ciphers, starting with the reverse cipher and really ending with a transposition cipher. And we're going to demonstrate how to build these in Haskell, as well as how to break them. And we're also going to learn some things about performance, and also sort of the difference between writing, thank you so much, declarative code and also more imperative code, and what the trade-offs there are. And so some of the examples as I give them, you may be thinking, huh, that's like that's maybe a strange way to do this, but really the exercises are intended both so that we can learn to build some of these primitives from scratch, and also so that we can learn how, what the exact benefits are of not relying on them and using some other structures that are available for us. So I wanted to talk, also just tell a story as we're starting off about my very first introduction to cryptography and cryptanalysis. So when I was in high school, I had a crush, and she and her best friend had a secret code that they used, and they would pass notes in this code. And she was very convinced that I wasn't as smart as I thought I was, or maybe not smart at all. And in what turned out to be a moment of arrogance, gave me a stack of these notes that she had written back and forth with her best friend, basically laying down the gauntlet. There's no way that you can decrypt this. Like, my secrets are safe. And I realized after, it's amazing what being young and in love can motivate you to do. And how, even though maybe I wasn't doing any of my homework, I sat and worked through all the possible combinations that these letters could have involved, and figured out, it turns out there's some pretty fundamental ideas to breaking ciphers that, there has to be basically, if you're using some kind of shift cipher, then there are statistically going to be a certain amount of E's in English compared to a number of Z's, right? And then also, most letters, in English start with a small number of words, like dear, hello, hi, dearest. And also that if spaces aren't obfuscated, or punctuation marks aren't obfuscated, then again, encrypted messages leave all kinds of clues in them. And so push came to shove, and I decoded this letter, and first conquered the code, and then asked this young lady out, and had a fantastic time watching her blush as she realized that the dumb kid who was playing guitar had cracked the code. And so really we're going to be doing some of the same things today with ciphers that are really similar to that one, that involved rearranging letters or transposing letters into other sequences. And this is a class for beginners, and so please, if I'm leaving you behind at all, raise a hand, let me know, and I will slow down or we'll dig in where we're at. And also, I really want to use today as a gauge to see where we're at as a group, to see what we can accomplish tomorrow. Tomorrow's where we take on the big guts of implementing what we call textbook RSA. And by textbook RSA, we mean that it is going to implement the RSA spec, but it's going to do so in such a way that leaves it vulnerable to attack. So it should be something that it can demonstrate to us what it means to build a modern cryptographic algorithm, but it is not something that you should ever use in production, right? So this is for education only, not for actual encryption of actual secret texts. Otherwise, you will be blushing the same way my poor young love was as all of your secrets are revealed to whoever gets a hand on them. I also wanted to move this beyond just sort of what maybe is done with a lot of beginning Haskell courses that are working with strings and lists, and work with some packages beyond just what's in the prelude. And so as we're manipulating text today, we're actually going to use the data.txt package, which has some significant performance and API differences from strings in Haskell, which, as was covered in the previous course, are simply aliases for singly linked lists of characters. We're going to start out by just working on some basics. And so what I'm going to do, and were y'all able to is anybody having trouble getting the project or getting started, or are we good to go? Okay. So I'm going to be walking through some beginning stuff, so we've got plenty of time, hopefully, while it builds. Yeah, so let's go. So the first cipher that we're going to build is just a reverse cipher. And we're going to do this in a couple of ways. And I want to introduce basically some just fundamental things before we go forward. And so I'm going to just create a new file in my source directory. I'm going to call it textybiz. And then I'm going to open it up in my editor. And then over in this other pane, which is also just in the same directory that I was before, I'm actually going to open up GHCI with stack.
Could you make the letters a little bigger?
Mm-hmm. Is that good? OK. So to start this off, I'm going to do a module statement. And it's important that the module statement has the same name as the file name. And then we're going to import a few things. So we're going to import qualified data.txt as t. And we're going to import qualified data.txt as tio. And who knows what this qualified keyword does for us? Yes?
Avoid collisions.
Yeah. So if you leave it out, if I leave this off, then by default, everything that is in data.txt, sorry, this needs to be IO, and data.txt.io, all of the things that they export will be brought into our namespace. Even though we've referenced it with the as t, that means that we can reference it directly as with the t. It's going to clash. And the text package strives to have, as much as possible, a very similar way of working with it as the strings do, which means a lot of the functions are named the same, which means that if you don't use qualified, when you try to use a text function, it's going to say, I don't know if you're trying to use the string function or the text function. And so you run into some trouble. So we're going to do qualified. And that's going to solve our problems. OK, so in order to just use text, we're also going to use a language extension. And this is going to go above the module declaration. And this starts like so and has language all caps and then is over loaded strings. And, oops, strings. And what this is going to do for us is this is going to let us use raw inline strings as if they were text values. And so I'm going to demonstrate what that works here. So if we give ourselves a little hello world type, and we give it of t.text, and then we say hello world equals hello world, we can jump over into our thing and see what have I got here. I said it was important, and I meant it. Got to have that name match the same thing as the file. TextBiz, not TextyBiz. Import TextBiz. OK. And then I'm going to quit this real quick and build real quick. And what am I doing wrong? Oh. Yeah. I think this is what's going on. That's not it. Let's go ahead and quit and see what I've... OK. I had a little clash there. Going to start over real quick. If you named your files correctly and your modules correctly, then you should be OK. Feeling better already?
Did you forget the text IO?
Yeah, I just was a little bit flustered, and so I wanted to make sure that it would at least build with the file name corrected. Thank you. OK. So, right. OK, we're in business. OK, so now real quick, I want to demonstrate using that TIO. So print hello world is an IO. However, if we try to do something like this with a regular put string line, and we see a problem. Could not match type t.text with a list of characters. Expected type string, actual type t.text. And so you're going to see this type of thing whenever you accidentally use a function that is not compatible with the text type. But luckily, the text package provides functions that are most always named the same and have the same output types as the ones that you may have used in the past, but accept text as arguments. And so, oops. So that was one thing that definitely, as I was getting started, tricked me up, because it feels here like we're able to use strings and text you know, one way or the other. But actually what's happening is this is just being converted to a text type. But that doesn't mean that every single function that has ever accepted a string in its entire life was also converted over. And so for functions that expect to operate on strings or on text, we must use the accompanying appropriate type. As far as joining these, we can also, you may, let's see, if we do something like this, joined, this is the way that we normally concatenate strings in Haskell. And if we try to do this with text, we're going to have a problem. Again, couldn't match type of car. What we can do is use the good old semigroup operator. And we can do that by importing data.semigroup. It's in Prelude already. If you do need to find it, you can find it there in data.semigroup. And there we should be good to go. And so just a few little things to keep in mind as we're using these, especially if you're used to strings. Then to find out how you can operate on these, you'll want to go to, also just in case you don't know, extension tabbycat, available for all your browsers, the absolute best software that has ever been invented. I mean, basically, we could spend all 3 hours doing this, and your money would be well spent. But if you're ever looking for something to make you smile while you're getting angry at the programs that you're writing, strongly recommend it. We've got a channel at my work called Important Tabby Cats for ones that are found that need to be remembered. The data.text here. Okay. Okay. Oh, also, I have some notes. I'm going to drop those in Discord as well. That may help. For getting through some of this. Okay, so you can kind of follow along here with the notes as we go, if you'd like. And that may help too if, okay, yeah, but you can go to the data.text package, and this actually has quite nice documentation. And you can see here, it has the functions that are available to work on text. And you can see that a lot of them are quite similar to what but they're made specifically for the text type. So as we're working on these exercises, if you're trying to figure out how to So beyond that, I want to make sure that we are OK with doing some simple pattern matching before we get too much further. So if we have something like the last class talked a little bit about data declarations, but So this is essentially just an if statement that is checking to see if we're in encryption mode, and it returns the string encrypt if so. Otherwise, it returns the string decrypt. Let's see. We're going to derive EQ, and we'll do show as well. OK. Deriving EQ, let's many other programming languages, because we can't do something like this and accidentally misspell it, right? But we can do pattern matching on these values here, which are called the data constructors. And that ends up looking like this, where we actually just say, in the case that we pass in encrypt, we return encrypt. And in the case we pass in decrypt, we return decrypt. And this is just a little bit, in my opinion, more idiomatic way to write in Haskell, and lets us just do some pattern matching. It's just a little bit more straightforward. And besides pattern matching on data constructors, it's also going to be important for this class to realize that we can pattern match on values themselves. So if we had, for example, a function that car to something, and we wanted it to do something specific when it took in the character A, I guess I'll call this so now, if I pass in A, we get my fave. And then this underscore here indicates to the compiler that first we want to match on anything, and we don't care what it is. We're going to throw it away. If we wanted to have other values in here, we could do so. And so now and with all pattern matching in Haskell, it's important to remember that the patterns are matched from top to bottom. So if we do something like put the wildcard first, we're going to get in trouble. And I think with that, especially with the excellent course that has preceded, we're ready to go into our reverse cipher. So this is going to be our first little exercise. And so first off, the text package has a function called reverse. Oops. Also important to know that if you want to use the text thing directly in GHCI, you can also import it just the same way that you would import it inside of your file. But what we want to do is we want to get practicing with our basic Haskell skills, flex some of our muscles, get a little bit practice in. And so we want to implement our own version of this. OK, so I'm going to go over a few functions in the text package that may come in handy, and then I'm going to cut you loose. And so the goal here is to write a function, reverse cipher of type t.text to t.text. And reverse cipher should take in something and return the x's reversed. So some functions that may come in handy. We've got length. This will take a text and return an int, which is the number of characters in the text. We've got take. This takes an int and a text and returns a new text, which is the number of the characters. And then we've got cons, which takes a character and a text and returns a new text with that character added to the front of it. And then one of my favorite things in Haskell, snock, which is cons reversed, both in the arguments that it takes and in the actual letters of the function, which I think is just always tickles me pink, which takes a text and a character and then returns the character to the beginning of the text. And we're going to be using these as educational purposes, but I want you to pay attention to this documentation that lets you know that first off, cons is more costly than the list counterpart because it requires copying a new array. And then snock, as in this copies the entire array in the process unless fused. Subject to fusion. We're going to be talking about fusion more later, but some of this is important. A lot of times when you get just barely outside of Haskell, you'll hear people warning you about the list type. And of course, singly linked lists have performance concerns, but every data type does. And there's no data type in the history of computer science that's a magic bullet that just improves performance because you use it. And so any data type, so it's important to know how to use text, it's important to know how to use lists, but you should only adopt a data type, particularly for performance reasons, if you do benchmarking around it. So don't just assume that because somebody one time, or a lot of people one time said strings are not performant in Haskell, that text is automatically going to be the answer to your problems. And also understand that you really need to learn how to use these data structures to make sure that you're using them performantly. Okay, so get at it. Write me a reverse. Has anybody got it yet? Who has an idea for the algorithm about how to do this?
So we can just use recursion to take one character from the beginning and then just cost.
Yeah.
Do it recursively for each character to read the new text, I suppose.
Yeah?
I was not sure how to get the code left.
Okay. Yeah, so the general strategy probably is that so you're going to have you're going to have the message that comes in, right? And let's say the message is really small and it's just a 3-letter word like the, right? So when the message comes in, you can go at it either from the front to back or back to front, doesn't matter. You can grab one character and create a new string and move it. So if you take the last character and then you put it at the beginning here, and then you take the middle character and you put it at the middle here, and then you take the first character and put it at the end here, then you can use recursion to take two structures, one a text of length n, and the other one an empty text, and swap them. And so your end condition for recursion can be when the input text is empty.
Can you use just empty double quotes for pattern matching?
Exactly. So we can pattern match on, we're going to do a lot of pattern matching. And it's always remember, we've got data constructors and values. And the empty text is itself a value. Yes. Absolutely.
I run stack JCI, load this file, but it seems that it doesn't pick up this input. So, for example, yeah, it works, yeah. But if I do just a T.
Yes. So it knows that data. So you can do actually right now out of the box. You can say data.text.uncons and do the whole thing. But if you want to access it as T, you need to write the same import here in GHCI to say import data.text as exactly. If you just copy that straight over.
And why doesn't it pick up from the file?
Because GHCI is only picking up what's exported from here, and the imports aren't exported. So the same way if you had two files, and one imported data.text, import qualified data.text as T, if the other one imported this file, it would have by default available each function, but it wouldn't have the imports. Because, does that make sense?
Okay, I understand that it's for a reason.
Okay. It's just to keep, if the imports were also exported, then at the end of a project, every single file would have access to the dependencies of every single other file. And so it's a way of keeping the dependencies internal while the functions that are needed to be exported can be used. Yes.
Is there a way to quickly overload the string also in GHCI?
Yes. So, so if you're using stack in the package.yaml file, you can add default extensions with overloaded strings. And then if you so there's a couple different ways to launch GHCI from stack. One is like this. If you do stack exec GHCI, then it loads it kind of independently without your project settings. And so then if I do this, it's going to be a car, and then, oops. But if you do stack GHCI directly, you'll notice that it loads a bunch of stuff, and then you'll see this data.string.isString p to p type constraint with a p, and that's going to be a sign that the overloaded strings is working. If you need to do that directly, I believe that type classes has a great reference. Here, Joy.
Concatenates at the end this character at the end of this thing.
I thought they had this out.
Yeah, with strings is much easier. Yeah, for me it was also easier to reason about simple list than this thing.
I'll take a look for it later, but there is a great reference on these. And so there's ways to do it without stack, but these are the kinds of things that I have a real hard time remembering. I kind of find a way of doing it and then just get it to work, but this is how I do it. Default extensions and overloaded strings, and then run GHCI with stack. Okay. Okay, I'm going to start doing something. So one of the issues that we have here is that our function takes one argument, right? But in order to use recursion, we need to have two arguments. Because we need to pattern match on the empty string. So a very common strategy for doing this is to write a little helper recursion function. And a lot of times I see people use the word go as a sign that this function is not doing anything except just helping us recur. And so this doesn't have a special name in Haskell at all. It's just like a way to say, we're going to do some recursion. And so what we can do is going to be the empty string. And so what we want to now do is we want to get into a situation where at the end of the recursion, these things are flip-flopped, where the first argument is empty and the second argument is full, right? So we're going to call this function like this. Now, you can define like so. Equals something. But the problem with this is that it really doesn't have any use on its own there, right? And so I think that it's better to use either a reverse cipher scope. That way, we don't have to worry about coming up with a million different names for the Go function because it won't worry about its scope leaking out in any other way to other parts of our project. We know when we want to stop, right? We want to stop recurring when the first argument is empty. And so whenever we get there, we can say that whatever came out the other end is done. And it's always great when you're practicing recursion to make sure that you handle that exit case first, because then you don't have to worry about the ugly specter of infinite recursion rearing its head and find yourself frantically mashing Control-C or Control-D and trying to remember which kill dash number is safe to use in your terminal and which one might get you into trouble. So let's say that our second version of this is where we've got an input and an output. So here, what I'm going to do is I'm going to use let to just define a little another little scoped variable inside of my Go here, and I can say L equals t.length input. And so now we can call Go again, and we can use t.take. And we want to get everything but the last character. So we can do L minus 1. And Yep, the reverse cipher is just the same thing as reverse function. It just takes in some text and returns it reversed. So a pretty simple cipher. And really, the only thing that a cipher is just an algorithm that takes in a message and scrambles it somehow. So there's codes and there's ciphers. Codes, and both of them encode an input text. But the difference is that a code is meant to do so in an organized way that is obvious from the outside. So you should be able to take a look at something like a code and be able to more or less easily determine the structure of the code from the message itself. Whereas a cipher is a code that tries to obfuscate the method of encoding along with the encoding itself. And so we could think about this with a computer language. We say we write code, right? You could probably look, I mean, depending on where you work, I guess I've written some code in my time that is probably also qualifies as ciphers as well. But good code, especially good, well-written code, should not obfuscate the intent behind it, right? But a reverse cipher, I guess you could argue, could fall both ways. But since there's nothing inherently useful about it, since it doesn't, for example, make the original text easier to transport or make or isn't suited to a particular domain, I would say that it's more of a cipher than a simple code. But so our first argument now is t.take L minus 1 input. And then we are going to do t.snock output t.last I. So first off, let's go ahead and save this. What did I do? Let me make sure that here, let's get rid of some of this other stuff. Oh, gotta have those dots. Okay. Issue here, type signature needs to have the double colons. If you leave that out, you're going to have a bad time.
Just quickly, you cannot use drop. Is that part of the
You can totally use drop. This is just a way of dealing with it. And let's see. And there we go. Looking pretty good. Okay? Perfect.